All right, let's get started. So we're going to talk about image staging. And so I think this is a topic where it first got people excited about computer visions because it's actually one of the first application that makes things work. So now everyone takes for granted. But I think it's a really good topic because later on you'll see how this single application ties many of these different components that we talked about so far, right? All right, so where are we now in the module 3? Okay, so we start module 3 by talking about the relationship between a point in the 3D coordinate world coordinate system XYZ, and then we will translate that into the camera coordinate system through this rotation and translation, and then you have a projections and to the camera coordinate system. And then you scale it and shift it so that you get an image coordinate system. Okay, so from the XYZ in the 3D point to XY in the 2D point. Okay, on image plane. All right, so these are the kind of camera to image transformations. And so we already talked about this. And then earlier we talked about how you could calibrate the camera. And the way you can calibrate the camera is that you have a known object and you take a picture of your camera on that known object. Okay, and the known object, you have the corresponding 3D locations. That's the known things, and the 2D location you can run your Harris corner detections algorithm to identify those key points. And then you want to solve these unknown things, right? What is the matrix? These numbers that can map the known 3D point positions into known 2D positions. And the way we solve this is actually kind of basically the number one method we use is that you expand these linear equations and then you write it down into a system of equations. And once you have this, you can pull the unknowns into a column vector and then write down the known coefficient on the left or the known coefficient on the right. And in this case, you can get this equation. And once you have this equation, you can solve this either through least square solutions or through SVD. Okay, so all these are we talked about in the previous two lectures. All right, so in the last lecture, we talked about the concept of vanishing point. A vanishing point is a parallel lines in 3D, but if you have a perspective camera, it will converge to a point in 2D, right? So based on a vanishing point, you can actually use the vanishing point positions to calibrate your camera. You can estimate what's the focal length and U naught V naught is, okay? And the way to do this is that you know the vanishing point in 3D here, and the vanishing and the kind of detected vanishing point in 2D. You can express in this way because you know the vanishing point, because you know the building are built in the kind of orthogonal manner, and therefore you know that you have orthogonality constraint. Like these vanishing points are pointing to orthogonal directions. 3 orthogonal direction in terms of X, Y, Z. All right. And then what we do is that you can write down the orthogonality constraints. And now you have this, you can cancel all the rotations here. And if you have a constraint for P1, P2, P3, then you have all the constraints like this. Okay. Then after this, it's just a bunch of algebra. You can to just show you the algebra operations, then you can kind of subtract these two equations, you get this, subtract to that equation, you get this. And if you do some high school math, you get something in the end like this, okay? Based on just the vanishing point, you can estimate your focal length, okay? And once you get the focal length and the U naught V naught, then you can come back and figure out what is the orientation of the camera with respect to the vanishing point coordinate. Okay, so you have this rotations matrix. Think about this rotation matrix is 3 columns, then one of the vanishing point is basically each of the vanishing point is either in the 1, 0, 0, 0, 1, 0, or 0, 0, 1 directions. Okay. So with this, you can, if you plot this x1 inside these equations, you get p1 equal to kr1, because 1, 0, 0 is it's basically if you multiply a rotation by 1, 0, 0, essentially what it does is that you just pull out the first column, right? Similarly, if you take the 0, 1, 0 column vector and pre-multiply this rotation matrix, what a 0, 1, 0 did is to pull out the second column of this, right? So you pull out these guys, and so now you know how to express the R1, R2, R3 as these guys, right? But the problem is that you still don't know exactly. Then you can solve for because you know this rotation matrix will have the property, right? That is the inverse of rotation is this, and each column and has unit norms. And then what you do is that you enforce that constraint, then you figure out the rotations. Okay, so basically, there are two main different methods. Either you take a photo, take your camera, capture a photo of a known object where you know the dimensions, then you can calculate the intrinsics, or you can use the vanishing point. But that assumes that you have a building that has satisfied this the so-called Manhattan assumption. That is, every vanishing point is orthogonal to each other, right? All right. Okay. So vanishing point is very useful for making use for us to as a perspective cubes. Right. So the main idea is that every lines, this is every line that draw from that vanishing point are parallel lines in 3D. Okay. What it means is that you have all these lines. The reason why you see that these guys are the same height is because that you know these are the lines that are parallel in 3D. Okay. Then here, like all these lines are parallel in 3D. Okay. So because they're parallel in 3D, so you can now use this to measure height from a single photo. If you have a reference, right? So you have a reference here, and what I do is I just draw. If I know the ground plane here, I can draw the bottom of the reference, and then to the object I want to measure is here, and I draw another line from that point here. At every point, every kind of corresponding these two lines are parallel lines in 3D. Okay, and because they are parallel line in 3D, if you can measure what the distance here, then you know what the distance here, right? Because they are parallel. Parallel means that every 2 points are the same distance. Okay, so you can use these cues to measure height of object from an image. Okay, so here you can see this is 5.3. So if you have a turtle here and same thing happens, you can actually measure the height of turtle by just using this perspective cubes. Okay, so now last time we also talked about the concept of cross ratio, right? If you have this, there's something that 4 points that doesn't there's some ratio between them that's invariant perspective, no matter how you look at these 4 points, right? So these 4 points are the bottom of the objects, the reference point, the top of object, and the vanishing point. Okay, if you have these 4 points, then you can figure it out. You can use this ratio to compute the measured distance. Okay, so imagine I take this is the actual physical world, and I capture a camera on this. So I get T, a reference point, the bottom of the object here, and the vanishing point. Okay, so in this case, sorry, I get these 4 points, right? So the idea is that because you can measure the image distance, right? How many pixels are there? and they are related by the physical objects, right? They're equivalent to the physical, the cross ratio on image and cross ratio on the physical world, they're the same, right? This is called something called projective invariant. They don't change no matter how you look at them, okay? So the image cross ratio is the same as this physical cross ratio. And with that, you could be able to measure height through this way, right? So I have this reference objects inside the things, even though I don't know what, there's no measurements on that things. But what I can do is that I just first figured out what is the top of the object on this reference, on top of this reference. So I get these points. And now I have these 4 points. I have this B, T, R, and the vanishing point. Okay. So now this is the height of the person. This is the height of the person here. Then I can compute the image ratio, cross ratio from this ratio will be the same as this ratio. Okay. And then you can use this to figure out what is the size of this edge. If you know R, I can figure out what is the size of edge. Okay. All right, so this is a quick overview of what we talked about so far. So you can think about this lecture as a kind of a review of what we have been using in module 2, module 1 and module 2 as well. Okay, so we have what we will be talking about is that in order to do the image stitching, we will need all these tools. We need camera models and basically the homography relationship, the transformation between planar points, and how do we solve homography of solving linear equations, and how you do the key point alignment, and how you do ransack. And then once you have that, all those things line up, how you do the blending, right? Blending, this is something that in the module 1. Okay, so how do we do the, so this topic includes all these components. All right, so let's look at the illustrations. So you have a camera and you take a photo, right? So this is a camera, you take a photo. The problem is that this camera has limited size of sensor, right? Your camera is like this, but you want to capture wide field of view. But your camera is not like a 360 camera. You don't have that wide field of view. So the idea is that can we computationally overcome this limitation? Okay, so now it's the concept, the idea is very simple. You capture a camera, a picture from one viewpoint, and you rotate the camera, and capture another picture. Okay, you capture a picture here and rotate the camera and capture another picture. So the hope is that if you can figure out how these two images are related to each other, then you can stitch them together. You can combine them into one single image. Okay. So, and this is where the correspondence comes in, right? So if I know the tip of this guy equals, so originally the first frame this is the plane of the image of the first image, right? And this is the plane. Now they live in different plane. All right, that the image lives in this plane, and the original image lives in this dashed plane. Okay, so we need to somehow map a point on one plane to a point in the other plane. Okay, and the way we do this is that we figured out the correspondence. Like this is the correspondence, and these 2 points are corresponding. Like you can see that they all point to the tip of this this term and this river bank. And then what you do is that you can just map this. See, this pinpoint means that there's a color here, and you can map this to the plane of the first image. Okay, And once you figured out the plan of this relationship, now you can extend what's not visible in the original image, right? For example, this point is not visible in the first image, but now you can actually extend this to the plan of first image, and this is how you kind of get an extended field of view. Okay. All right, so that's a kind of simple illustration of how like image stitching works. Yes.
And hit stitch, instead of just rotating, can you also translate it and then hit stitch as well?
No, so you can actually try if you take your like a cell phone panorama app, and you will find that you will get worse kind of stitching if you when you capture the camera and you kind of use kind of translate it, then you will also be the stitching will not be great. Okay. The reason why is that when you translate it, you have something called parallax, and that parallax basically means that okay, so something is closer to you will move faster than something that's farther from you. Okay, so you have something called parallax, and that parallax cannot be explained by a simple transformation. Okay, so when you do the translation, you do the camera rotations, everything will move the same way, no matter what the distance, right? So you don't need to figure out the depth, right? So yeah, so we will talk about what's the relationship. There's also another set of relationship between two frames that are captured by translating camera, and that's the basics for stereo regions. Okay.
Is there like a minimum set of points that the two, I guess, need to have in common?
Right. So as we talk about, like these are related by a homography, and that has 8 degrees of freedom. You basically need to figure out 8 numbers, and like think about if you have every pair of correspondence will give you 2 equations, and you have 8 unknowns. How many pairs do you need? 4, right? So this is why you have 4 pair correspondence. Then you can figure out the homography. Okay. All right. So here's a problem setup. It's actually kind of very, very simple. We use this the very simple things of the camera. So if I have a 3D point X, right? I have a 3D point X, and that 3D point X is projected onto the first camera through this equation, right? Through the KRT, okay? And correspond to these equations. And now I have I have a second camera, and the same 3D point gets projected on the second camera. So I have X and X1, right? So the same point projected to image 1, projected to image 2, okay? And we said that there's no translation, so which means that essentially you take a photo, you have this photo, and the way you take a panorama is that you pivot from this camera phone and you only rotate it, right? You don't have translation, okay? And what will happen here is that because this T is not there, and therefore you just replace this, you can figure out what the relationship between X and X1. X and X1 can be described by this. Okay, so basically means that if I have 2 images that are captured by rotating camera, then the correspondence between all the points in image 1 and the corresponding point in image 2, they can be described by a single 3x3 matrix, the H. Okay, and the H is fundamentally has these parameters. Okay, fundamentally, there's only 4 unknown parameters, 4 degrees of freedom. Okay, but because this is 8 by 8, 3, and it's up to scale, so it's only 8 degrees of freedoms. So it's only 8 parameters. So you need 4 pairs to solve it. Okay, but later on we'll talk about if this is just a convenient way to solve for edge. But once you have edge, you can actually get a better estimate if you really solve for the K and R, like the intrinsic points, these parameters. Okay, so we have this this relationship, and then now we want to figure out what that transformation is. All right. So a couple words about homography. Like this is a kind of an it's also called projective linear transformation. Essentially, it's a point in 2D and mapped to a point in 2D. Okay. So there's a couple of examples where this will happen. Like the first example is that you have a 3D surface. Any 3D surface, planet surface, it's a point on a plane. And any point on a plane, you can use they are related to a homography. Okay. So one application is that you have a camera, and the camera is also an image plane, right? You project something onto an image plane. Okay. So any surface you can project onto the camera, and which means that you can use this as a rectification. Okay. So here's the example. Any surface, any 3D surface, it's any 3D planar surface, right? A plane and plane in 3D. If you have 4 points, you can map them onto the camera coordinate system. So you can see that this is as if you are looking up from the top. Okay, you can so rectify this. Okay. So all these transformations are described by a 3x3 homography matrix. Okay, so basically it's a 3x3 coordinate transformation. I give you x, y, 1. You will apply the 3x3 matrix to give you x prime, y prime, 1. Okay, so here's the example of like commercial example of how you can apply the homography matrix to map from everything, any content to any planar surface. Let me see if I can do this. This is a very old HP commercial. That's obviously they are trying to sell more printers. All right, so you get the idea. So this is how wait. All right, so this is how they because you can map every planar object, planar kind of everything onto a planar object. So that's why they can, as if they are when they hold a planar board, you can perfectly map that onto that. Okay. All right. So how does the overall image stitching algorithm work? Right. So you have two images. Let's say start with image 1, image 2, and you want to basically match image 1 and image 2 so that you can walk this image 1 and 2 to the image 2 to image 1. Okay. So you first start by detecting key points, right? Image one, image two, independently, you run the difference of Gaussian algorithm to explore a different scale to detect points where there are salient in not just x, y location, but also scale, detect feature points. And for each regions, you try to seek features, okay? And then you have this key point matching, right? So you have a set of points in image one, a set of points in image two. And we talk about you want to have you want to build a correspondence, right? To see which image features in image one match to the feature in image two. And the way you do this is that you don't want to just run the nearest neighbor, right? So this 10 point, you find the nearest point in the nearest feature in image two. The reason is because that you will run a lot of post positive. You will have a lot of repetitive structures. So what you want is to find not just a one nearest neighbor, but two nearest neighbor, right? So the idea is that you want to make sure that the ratio of the distance between the point to the nearest neighbor and the ratio and divided by the distance to the second nearest neighbor, you want to make sure the ratio is small. And why is that it's small? Is that it means that if it is small, which means kind of intuitively, the second nearest neighbor is far different from the first nearest neighbor, which means that the match is very confident, right? You are very confident that this is a distinct match, right? You are not confused by plausible matches. If this ratio is close to one, which means that the first nearest neighbor, even though the distance is small, maybe the second nearest neighbor is also small. Then it means that it's ambiguous match, right? So you won't be able to figure out whether this is a good match or not. So that's why it's a good heuristic. It's proposed in 2001, and 25 years later, we still haven't have a better heuristic than this. Still used today. So it's pretty amazing. Yes. It not really ICP. In ICP, we don't have the correspondence, so we have to guess correspondence, right? So in ICP, we only have the point sets, right? A bunch of 3 points, and we have a bunch of 3 points here. In this case, I don't have the descriptions about the 3 point, and therefore I couldn't build the initial correspondence. I can only use the position itself as the feature to match. But here, I actually do have the local appearance of that point, that C features, and therefore I can rely on the C feature to do the matching. Okay? Yeah. 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 This is just initialization. I don't know the transformation between them. So, but I know that if I will have a better correspondence if I just offset them at the same location. Yes. Yeah. But of course, you can keep track of the transformation, what you did. Yeah. 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 All right. So once you met better matching, what you get after this, you will have a bunch of matches that says, okay, feature number 11 match to image 1 match to feature 25 image 2, feature number 19 match to feature number like 37. Okay, so you have a list of pair of matches. All right, so once you have these matches, then you can estimate the for every 4 points you can compute homography. Okay, but you, even though you have this 2 nearest neighbor rule, it still sometimes you still have a lot of outliers, and therefore you need to run RenSec to make sure that you don't run the wrong bad matches. Okay, and once you figure out this is the robust way to figure out the relationship between the features correspondence. And once you have this, then you combine the images. All right. So this is the high-level sketch of the the image stitching algorithm. All right, so let's dive in each of them a little bit in detail. Let's say first, if you have a 4-point match, how do you, if I have a 4 match points, how do you solve for the correspondence? So the idea is that I use something called direct linear transformations. It's basically this one algorithm that we have been using so far, right? So you have this mapping correspondence. This is a UNA, VINA, W. It's in coordinate. It's in homogeneous coordinate system. So you have a scaling here. And what you do is that you just feed in this. You just build this mapping. UNA, VINA. This x1 equals h times x. Then you just expand this and pull the unknown vectors into one thing, and you get something like this. Okay. So what you do is that you just put this in, like all this unknown is a column vector and this. So every pair correspondence give you 2 equations in these things. So essentially what you have is that every pair you give 2 equations. And if you just have multiple pairs, then you have this AH equals 0 problem, right? And then what you do is that you like the solution is taking the SVD of the matrix A and take the eigenvectors correspond to the smallest eigenvalue. Okay, so you take these eigenvalues, and this is how you solve it. Okay, and you get the H out. All right. So one thing that people found is that if you look at this guys, this A matrix A, you'll find that it has the number, the entry in the number in this matrix A has all these coordinate pixels, right? So when you detect features, these are the features of these are the locations like U and V. They are the pixel locations. So for example, this could be 300 and this could be 500 and this so on, right? So what you'll find is that this matrix A, they will be like these are the coordinate positions of the image pixel, feature pixel for image 1 and image 2. But if you see that these 2 points are multiplied together, right? So what you get is that this will be like -1, 0, 0, 0, and this guy could be 500 times 500, okay? So you will get something that's very imbalanced, right? This matrix has a lot of like small numbers and very large numbers. And this will cause the numerical issues. So what we do, what we can address this is that before you apply this, the key details is that before you apply the DLT, you first normalize the points, right? So of course you have a key point, you still have a key point correspondence, but you first figured out what's the transformation that can translate the points and scale the points so that this x tilde, this new point set is 0 mean and has a univariance, okay? So the average distance is square root of 2, basically kind of x and y, they are univariance. So this will lead to a better like numerical stability when you solve for the edge using direct linear transformation. So this is called normalized DLT, right? So you first take the point sets and you normalize them so that they are 0 mean and kind of the variance is just 2, and you do so for the points from one image and a point set from the second image. Okay, so you have these transformations. And once you have solved that, you compute the DLT, you use a direct linear transformation based on these 2 point sets in the normalized domain. All right. But what we really want is to be able to map a point from one image to another image, the actual pixel location. So this transformation is this in the normalized domain. So I need to unnormalize it so that I can use it. Okay. So the way you unnormalize it is this, right? So because this is coming from this transformation, so you can modify this transformation and take this inverse, and you get an unnormalized version. Okay. So once you have this, you now have the relationship in this. So the idea is that you could directly solve for h using the original coordinate system, but that would lead to numerical stability. Therefore, you first normalize x and x1, so and then you solve for that the transformation h in the normalized domain, and then you unnormalize it. Okay. So that's a simple trick that can make everything work robustly. All right. So once we have this, but this all of this is computing with just 4 points, and these 4 points are obviously inliers. You assume they're inliers. So how do you deal with outliers? Because even with the feature matching, even with the two nearest neighbor rule, we cannot guarantee that every point pairs are the inliers. So some of them are still like random matches. So how we do this? As we talked about earlier, we basically first choose a number of sample n according to like how many points you need, how confident you are. Then you every time for every trial, let's say if I run this samples for 100 times or 200 times, for every time I randomly sample four pairs of matches. Okay, around 4 pairs of matches, and then I compute it with the H with the normalized DOT. Okay, so normalized DOT is an algorithm within RenSec, right? Every time I sample 4 pairs, I use the 4 pairs to estimate the normalized DOT. So this normalized H is just a hypothesis. Like I don't know whether it's right, but one way I can check how good this is to check how many point pairs can this H explain. Okay, so what I'll do is that I take all the point in image 1, and I apply this edge, the edge I just solved, to get an x plot. Okay, and I check if this x plot actually very similar, if this point is actually very similar to the actual correspondence. Okay, and if, like say, typically you count how many point pairs can this explain, can this edge explain. Maybe in the end, you have say 500 pair correspondence, right? You detect C features, thousands of C features, and after correspondence you get 500 of them. Okay, 500 pairs, and you only need 4 to estimate a homography. And then what you do is that you go through all the 500 points in image 1 and compute the map points in image 2, and you check how many of the points actually line up with the correspondence. Maybe in this case it's only if it's not a good homography. Maybe one of the point pairs are wrong matches, then you'll get something that's very low, right? Because your homography cannot explain the rest of the transformation. Okay. So you repeat this, but if it's actually correct, then typically you can explain this. You can compute a lot of inliers. You basically repeat this n times, and then pick the one. Every hypothesis you try, you will get a score, right? And then in the end, you pick the one that's the best. Okay, pick the one with the most inliers. All right, so this is how you apply homography in the context of image stitching. All right, so we talk about starting from images, detect C features, build matches, and then and run ransack with normalized DLT to find actually what is the transformations. Okay, so this is what visually what it looks like. So imagine you want to capture kind of mountains. In this case, initially the match points are like this, right? So I didn't draw the matching point, but you can see that obviously it's not right because these points they shouldn't have match points here because they don't appear in this image. But still, there's some matching, wrong matching, right? But you don't know what is correspondence, right? So what actual correspondence is. But once you have this, you can figure out, okay, these are correspondence matches. All right, so all these are kind of matched together. And once you figure out the matching, you can run the DLT to figure out what is the transformation between them. And with the transformation, you can then kind of move one image onto the other image, right? This is how you can get that alignment. Okay, make sense so far? Yes.
How do you go from having the long matching
So you run this for ransack because you know that the key idea is that you know the correct matches can be explained by the homography. Okay, so so the right homography will have the most inliers, and therefore that's how you can get rid of the incorrect matches. Because now you can see that there are many incorrect matches at the beginning, right? So all these points are impossible matches, right? Because you don't see them in the first image. Okay. All right. So how do you do this? So this is where yes, sorry.
So for when you were using ransack for this, it requires like pre-existing match pairs to work. Right?
Pre-existing match pairs. Yeah, I need C features from both sides, and I need to run the two nearest neighbors to match them.
And that's when it like after you run the two nearest neighbors, then it applies and actually checks what are ambiguous, like what are not matches, and it joins them together.
So once I did a two nearest neighbor match, I will give you basically a list of candidate matches. But at that point, I still don't know what is the actually good match. It could be a distinct match, but it could still be wrong, right? So I want something. There's no guarantee that it's going to be the good match. And in order to figure out exactly what the good match is, you need ransack to figure out the inlier and outliers. Yes.
When you do the DLT operation, this should be exactly for samples with each or do we use more samples?
Right, that's a good point. So if you imagine this, if you use more samples, you actually can get more accurate result, right? But when you run this, you don't actually know which pairs are correct, which pairs are not correct. And initially you don't know. You don't have an algorithm. You don't have a human to eyeball. Oh, these points are right. These points are wrong, right? So it's all automatic. So which means that the 4 points, that is the minimum samples you need to get a hypothesis, right? A guess that is like based on the pairs, you can figure out the homography. And because you have some like outliers, and so that is a big. If you use 4 points, they will give you the more possibility to get you the that is that the points you samples are all of them are inliers. Okay, if you use, say, as a sample, I can sample 10 pairs and add them homography, then the probability of that all 10 pairs are inliers is going to be lower, right? Which means that you need to draw more samples, more trials to get a good estimation, to get a good hypothesis.
It's a minimum.
Yeah, so that's why you need to keep the minimum.
Because we don't know the property.
Yeah, you don't know the inlier outliers. Okay. And that being said, a typical practice is that once you figure out all the inliers, maybe imagine that you have 500 matched pairs, and then with this 100 matched pairs, you may figure out, oh, maybe 300 of them are inliers. Okay, so that actually can be well explained by this homography. Then the rest of 200 are outliers, just random matches. Okay, so at this point, you may ask, like, why do I trust my homography estimation from just 4 pairs, right? So what we should do at this point is that I should take that 300 inliers and jointly solve for the edge. Okay, remember that when we solve an edge, the way we solve edge is that every pairs give me 2 equations, right? And again, 8, and in total I get 8 equation and can solve this edge. But what if I have 300, right? 300 and it becomes 600 rows. So that becomes a much more reliable approach because you are solving an over-determined system to solve that edge. So that's a very common approach. Once you figure out, use ransack to figure out inlier outliers, you use all the inliers and solve for least square solution. Okay, make sense? All right, so everything is kind of connected. All right, so to do this step, kind of once I figured out the mapping from one image to another image, I need to kind of walk this into this one, right? So here I need to make a decision on what the projection surface how should I project, which surface should I project the image onto? Okay, there are many choices. The simplest choice is the planar mapping. Okay, so here's the illustration. So I have this focal length of this red image, and what I do is that I rotate and capture another image, and then I can just project them these points, this image onto this image, okay, onto the first image, and I get a extended view. Okay. So here's what happened, and this is the result. And of course, you don't like this black pixels, so what you do is that you just crop them. So this is the outcome. So planar projection has some benefits, right? For example, every straight line in the image will remain straight. Okay, so you won't see the kind of curved line in the image. But there's some drawback. Can anyone tell me what things you don't like about this? Yes. The resolution is a little bit off. Yes. Anything else? If I want to capture, yeah. Yeah, that's another problem we're trying to solve later. This is some obviously there's some because I take the picture and then that picture, the camera will have automatic bias and gain adjustment, so they don't really color is not there yet. But this is a separate problem we'll talk about. Any idea? If imagine that I want to capture a wide field of view, right? Maybe I want to capture a kind of street, maybe kind of 180 degrees field of view. Like this fundamentally cannot happen, right? Because I don't have a trend. I couldn't for all the for images that are further away, it will get projected onto very, very far, right? So it gets stretched and stretched for these regions. So it's really not great to do that. Okay, so you can partially see this part happening, right? So you see that a further field of view, you get stretched more, you get more distortions. Okay, so this is not great. So a more popular approach is called cylindrical mapping. So the idea is very simple. Like you basically you draw a sphere around this, and then you just compute every pixel of coordinates. Like what's the coordinate on the sphere, and you just map them onto this sphere. And this way, you allow you to capture the full 360. Okay. So here's another kind of cylindrical examples. And this way, you don't have that distortion. But you also like this kind of mapping. It doesn't preserve the straight lines. Okay, so this is the pros and cons. Okay, so these some examples and all right. So, but all these application right now is we are only talking about two images, right? One image and the second image. But how? What if I just capture a bunch of photos and in my photo album, and then I want to kind of automatically reconstruct everything with panorama. So this is the applications. So I want my photo corrections just dumping, and you automatically recognize which images are part of the panorama, and you want to kind of create these kind of collections. So this is this is applications building upon what we have. So what you do is that you have n images, extract C features, and then from all images, and then for each one of them, you match the features from all of them. Let me just show you the visuals. So once you kind of from images and you find the nearest neighbors for all the images, okay? So you can find that, oh, these images match to each other and so on. And once you have this, you can cluster them so that these images are matched to each other and so on. And now you have this, then within this one, you can start to build your panorama. Okay. All right. So as we talked about earlier, that the edge is kind of overly complicated things, right? They have 8 degrees of freedom, but fundamentally that edge is only because we treat edge as a kind of unknown entity, right? But edge actually comes from this intrinsic parameters k and rotation, like 2 rotation difference, right? So if you express this in terms of rotation difference and this k, and you can directly solve these parameters and want to make sure that the solve these parameters such that the reprojection error is the minimum, right? Basically, the feature correspondence will be very close after you do the mapping. Okay, so here's the process. It's called bundle adjustment. The basic idea is that I start with single image, and every time I add image, I try to find, I just kind of adjust everything, adjust all the like rotation and intrinsic estimation so that they align well. Okay, so here's the process what the process looks like. Okay, every time I add an image, every time I add an image, I will correct this things. I add an image and I match this. It's iteratively optimize everything. Okay. So this is the process. Like it becomes like so. Previously we talked about this just so the previous approach about one image and match to another image, that is just the inner loop of this algorithm, right? That's just the initialization. Once you have found the edge, you can figure out kind of the process. And once you feeding like hundreds of images in, then you get something like this. Okay. Right. So so you can see that it's pretty elaborate process, right? If we talk about the DLT, but you cannot just use the DLT itself, you have to normalize it, and unnormalize it. And then you can also not just use the normalized DLT directly. You have to run a rensec on the outer shelf. And then once you run the rensec on the outer shelf, you still need to do this iterative process to optimize it. Okay. And up to this point, it's still not done, right? So the obvious problem here is that like from image to image, like nobody will like this image, right? Because they are very strong scene, right? So you need to make sure that you need to have some way to blend them together. Okay. So this is a kind of the final step, right? Once you find the matches, optimize the things, optimize transformations, and then you can put everything together. But now you need to take care of the color difference, right? So there are multiple different ways, but here's a kind of simple approach, right? So if you have an images 1, image 2, what you would simply do is that you just make sure that, okay, everything is close to image 1, then you take the pixel from image 1, imaging is image 2, you take a pixel of image 2. Or you have something like a linear transition between them. Okay, you have a linear system transition between them, and you can composite them together. So we talk about this. I think Yao Zhi talked about this in the when we talk about Laplacian pyramids. Okay. There's some complicated methods that's kind of, if you have all the images line up together, you can kind of have some algorithm that can find where should you cut through the thing so that you can hide the artifacts. All right, so one simple approach that you can do first is that you can do the simple bias and gain adjustments. Basically, you have two images line up together. They have this seam, okay? They have the seams. What you do is that because you know which pixel overlap with which pixel in image 1 overlap to which pixel in image 2, then you can compute maybe the ratio between their intensity. Then you can apply the ratio to image 1 or image 2 so that you can kind of compensate that things. Okay, so you get something like this before and after, right? So it gets I would say a slight improvement, but it's still not there. It's still not resolving the whole thing. And it turns out the most effective method that people come up with is called it's used Laplacian blending. All right, in this case, it's called multi-blend blending, but basically the same thing. So here's the result. The main idea is that Laplacian blending is that you want to blend the low frequency components slowly and blend the high frequency components fast. Okay, so that's the key idea. And when you apply this in the image blending, here's the result, right? So this is the before and after. Okay, so you can see initially you can see a very clear scene, but if you blend the low frequency components fast and add the high frequency component that's sharp, then you get something like this. Okay, you can see a very clear difference, right? And this is very close to the actual output. All right, so yeah, we talked about this before. So the main idea is that, okay, you basically have a bunch of you have a Gaussian pyramids, and then you have this mask. Okay, 4 images you want to line up with you want to create a single panorama. So you have all these kind of low frequency components, mid frequency and high frequency. And then what you want to do here, you can see that this is a transition. This is the transition weights. Like you can see the high frequency component is very sharp, and low frequency components are kind of blending smoothly. So this will prevent something called ghosting, right? So if you just use the linear blending, what will happen is that the same people, because people won't, if you have multiple images, the people won't stay still, right? They will be slightly off. And in this case, you will see that some ghosting artifacts here, okay? And if you use this multi-blend blending, you get something like this, okay? Much sharper results. All right, so you put everything together in terms of blending. here's the results. You start with without bias and gain adjustment, because every time you capture a picture, your camera will automatically adjust the bias and gain, right? So when you, especially you capture close to the light source, like a sun here, right? So you see that, oh, this is a very harsh scene, okay? So once you can adjust the bias again, you get something closer. And then if you apply the Laplacian blending, you get the final results. Right? So these are kind of the steps for you to improve this. All right? So as you can see, this single application involves to build this single application. It involves all the things we talk about, right? So how you kind of use filters to detect features, describe C features, and then do the matchings, and then build the correspondence. You need to understand the cameras to know the relationship between one frame to another, and then figure out the use dual stack to find the matches. And then once you have all the matches, you need to use the blending to blend them together. Okay, any questions so far? Yes. It's this. Okay, so it means by using the Laplacian pyramids, like this is the blending ways. Okay, here. So if you have a lower frequency component, this is like a higher in the pyramids, like you have a smaller image, right? But your blending speed is the same, right? So imagine that this span for 5 pixels. A 5 pixel is a very large area in the low resolution image, right? But it's a very tiny regions in the high resolution image. So what you do is that you would use, let's say, 5 pixels blending, but you will apply this blending in all the pyramids. So high frequency domain, you blend fast, okay? And the low frequency domain, you kind of blend slowly, okay? So that's why you get something that low frequency domain, you don't feel there's any sharp changes. And high frequency domain, you get sharp changes so that you preserve, you don't have this ghosting artifacts. Okay. So the end result is like this. They give you linearly blend everything, it'll give you something like this. If you decompose into frequency domains and using Laplacian blending, you get something like this. Okay. All right. So all these are kind of the algorithm that's basically take arbitrary images and then you can stitch them together. But when you actually build applications, let's say when you build applications, like you say I have this iPhone, then what you do is that it's not arbitrary images. You are actually capturing the panorama at the same and while you reconstructing the panorama. Okay, so what you do is that you're not taking individual images. So this is a kind of, they have a pattern out there. So this is why we sort of understand what they're doing. Okay, so here's what they did. Like they are not actually capturing individual images. They are capturing a video, right? So they capture images at 30 frames per hertz, 30 frames per second, or 30 hertz. So every second 30 images. Then they also don't use the entire image. They only use the center eighth section of the images. Okay, so they only to prevent, because images at the border, their quality is lower. They usually have some distortion. So they only use the center parts. Okay, and then they will have alignment. So there, the alignment is also very interesting because you don't really need to use C features to align from one image to another because they are moved very slowly. Okay, so what they did is that you have this their cell phone have the accelerometer how do I spell this accelerometer? Okay, so basically they have a gyro, so they understand the acceleration in terms of rotation and they have this built in. So you can use that signal to help you to find the matches. Right? So initially they'll give you a pretty good initialization to find the match, and then they use cross correlations. So we remember that we talked about in the temporal matching, they use cross correlation of these patches to find the rough matches. Okay, and they will use KLT trackings and KLT tracking based on this to really pinpoint the actual offsets, because cross correlation can only give you the pixel level accuracy, but what you really want is the sub-pixel accuracy. So you use that as an initialization and then run Lucas candidate tracking, like what you implemented, and then once you find the tracking, you can figure out the transformations, and then you'll do the blending. Okay, and there's some details here. Like for example, when you capture this, they also run a face detection algorithm behind, so that they avoid the blending of faces. Right, so your faces, you want to make sure that they are not they are not blurred, and make sure they select the good image face shot to do that. Okay, so it's also a very complicated system to build these things, but you can see that they're not really kind of random magical things. This is all the components that we have covered. Okay, all right. So things to remember about these things. So homography related to in rotating camera, right? So if I have images they're captured by rotating camera, they are related by a homography. And you can recover the homography by ransack and normalize DLT. Okay. And once with that as an initialization, you can solve for the minimize for reprojection errors using the bundle adjustments. Okay. And you need a bunch of details to really make it look nice, like blending. All right. So in the next lecture will be a midterm exam. We will cover the module 1 and module 2. And then after that, after come back, we will go over the stereo visions, where now the images are not captured by rotating camera, but also translated camera. Okay. All right. Thanks.